students, as a part of engineering chemistry first unit, that is molecular structure and theories of bonding, today I am going to explain you about the molecular orbital energy diagram of oxygen molecule. Now what is oxygen molecule? O2s oxygen molecule. O2s oxygen molecule. Now since O2 is oxygen molecule, what are the atoms which are present in this particular oxygen molecule? Oxygen atom, two oxygen atoms. So we have to talk about oxygen atom. Now what is the atomic number of oxygen atom? Atomic number is 8. Atomic number of oxygen atom is 8. Since the atomic number of oxygen atom is 8, how many electrons will be a part of oxygen atom? 8 electrons will be a part of the oxygen atom. And this oxygen molecule comprises the two oxygen atoms. So totally 8 into 2, totally 16 electrons will be a part of oxygen molecule. So totally 16 electrons will be a part of oxygen molecule. Now what is the electronic configuration of oxygen atom? Electronic configuration of oxygen atom is 1s2, 2s2, 2p4. 1s2, 2s2, 2p4. 1s2, 2s2, 2p4. Right. Now this is how we can construct the molecular orbital energy diagram of oxygen molecule. On one side of this particular energy diagram, we have to consider the atomic orbital of the first oxygen atom. On the other side of this particular molecular orbital energy diagram, we have to consider the atomic orbital of the second oxygen atom. And in between there will be the molecular orbitals. And do remember, students, that the filling of electrons either in the atomic orbital or in the molecular orbital totally depends upon the three rules. The one is Aufbau rule, which states that the electrons are filled either in the atomic orbital or the molecular orbital in the increasing order of energy level. Next, Pauli's exclusion principle, which states that maximum number of electrons in either the atomic orbital or molecular orbital are 2. And Hund's rule states that the pairing of electrons won't take place until or unless each and every atomic orbital or molecular orbital is filled with the one electron of the same energy level. And we have to remember the two postulates of the molecular orbital theory while constructing the molecular orbital energy diagram of any of the molecule, students. The first postulate of molecular orbital theory and second postulate of molecular orbital theory. What is the first postulate of molecular orbital theory? Atomic orbitals combines to form the molecular orbital, and the second postulate of molecular orbital theory is the number of molecular orbitals formed is equals to number of atomic orbitals combined. So accordingly, two 1s atomic orbitals of the two oxygen atoms are combined to form two molecular orbitals, out of which one will be associated with the lower energy level or lower energy, which is sigma 1s, and another one will be associated with higher energy, which is nothing but sigma star 1s. In a similar fashion, two 2s atomic orbitals of the two oxygen atoms which are a part of the oxygen molecules combine to form the two molecular orbitals, out of which the one will be associated with the lower energy, which is nothing but sigma 2s, and another molecular orbital is associated with the higher energy, which is nothing but sigma star 2s. In the similar fashion, 1, 2, 3, 4, 5, 6, totally three atomic orbitals of the two. In fact, 6, 1, 2, 3, 4, 5, 6. 6 atomic orbitals of the two oxygen atoms combine to form 6 molecular orbitals. The 1, 2, 3, 4, 5, 6. And here if you see, the sigma 2pz is ahead of pi 2px and pi 2py. Pi 2px and pi 2py. Whereas in the case of the nitrogen molecule, pi 2px and pi 2py were a head of sigma 2pz. Now what is the reason? I have clearly mentioned in one of the video. The description of that video is given in the description box, or the link of that particular video is given in the description box. Please do watch the video. There are two orders we have to follow for filling the electrons in the molecular orbitals of a molecule. Up to 14 electrons, one order we have to follow. Beyond 14 electrons, we have to follow another order. What is the reason why we need to follow one order for the molecules containing 14 electrons and a second order we have to follow for the molecules containing more than 14 electrons? I have clearly explained in that particular video. Please do watch that video, and the link of that particular video is provided in the description box. Now let us fill the electrons in the atomic orbitals first. Let us fill the electrons in the atomic orbitals. So how many electrons are a part of 1s, 2 electrons, 2s, 2 electrons, and 2p, 4 electrons. 2p, 4 electrons. So 1s, 2 electrons, students, 2 electrons, 2s, 2 electrons, and 2p, 4 electrons. So the electron filling depends upon the three rules: Aufbau rule, Pauli's exclusion principle, and the Hund's rule. Accordingly, you have to fill the electron. 1, 2, 3, 4. 1, 2, 3, 4. In a similar fashion, let us fill the electrons in the atomic orbital of the second oxygen atom. That is 1s2, 1s2, 2s2, 2p4. 1, 2, 3, 4. Right. Now we have filled the electrons in the atomic orbitals of the two oxygen atoms. Now what we need to do? We have to fill the 16 electrons which are a part of the oxygen molecule in the molecular orbital. 16 electrons. In the similar fashion as we filled in the atomic orbitals of each and every oxygen atom. And follows the three rules, same rules: Aufbau, Pauli's exclusion, and Hund's rule. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. 15 and 16. So in this manner, we have to fill the electrons in the molecular orbital of the oxygen molecule. Right. So now, what sort of information we can read from the molecular orbital energy diagram, students? First is molecular orbital electronic configuration, bond order, bond stability, and the bond length. So first, molecular orbital configuration. So what is the molecular orbital configuration? Molecular orbital configuration. What is that, students? 1s2, sigma 1s2. Next, sigma star 1s2. Next, sigma 2s2. Next, sigma star 2s2. Next, sigma 2pz2. Next, pi 2px2. Next, pi 2py2. Next, pi star 2px1 and pi star 2p/1. Now, unpaired electrons are there in the molecular orbital of the oxygen molecule. But in the first class, that is the class which I have explained on molecular orbital theory, I have clearly explained that based upon the structure of the oxygen molecule, it is diamagnetic in nature, but actually or practically it is paramagnetic in nature, and paramagnetic nature of the oxygen molecule can be predicted by molecular orbital theory by drawing the molecular orbital energy diagram of oxygen molecule. Now, as in this particular molecular orbital energy diagram of oxygen molecule, as the unpaired electrons are there in pi star 2px and pi star 2py, we can say that oxygen molecule is paramagnetic. Oxygen molecule is paramagnetic, but according to its structure, diamagnetic. But practically it has been proven that it is paramagnetic, and it is evident from molecular orbital theory, which can be shown with the help of a molecular orbital energy diagram of oxygen molecule. So it is paramagnetic. It is paramagnetic. So how we can say that it is paramagnetic? If unpaired electrons are present in the molecular orbitals, paramagnetic. If unpaired electrons are not present, then it is diamagnetic. Unpaired electrons are present, so it is paramagnetic. Now, what we need to do? We have to calculate the bond order. So, bond order, what is the formula? Bond order equals to 1/2 Nb minus Na. Nb minus Na, which is equals to 1/2. Right. Nb means what? The number of electrons present in bonding molecular orbitals. And what is Na? Number of electrons present in anti-bonding molecular orbitals. That already I have explained during the explanation of molecular orbital theory postulates. Now let us count the number of electrons in bonding molecular orbitals. Right? So 2 here, 4, 6, 8, 10. So totally 10 bonding molecular orbitals. So what about anti-bonding molecular orbitals? That is, how many electrons are there in anti-bonding molecular orbitals? Anti-bonding molecular orbitals are denoted by star. Star. Let's see. This is star. So 2 here. This is star. 2 here. 4. Next 5. Next 6. Because these are stars. Stars are nothing but anti-bonding molecular orbitals. Totally 2, 4, 5, 6. So 1/2 into 10 minus 6, 4, which is equals to 2. So as the bond order is equal to 2, we can say that the double bond exists between two adjacent atoms of adjacent oxygen atoms in a oxygen molecule. So double bond exists between two adjacent oxygen atoms in a oxygen molecule. Now, when we are getting the information about the bond order, and as there is a directly proportional relationship between bond order and the stability of the molecule, and as the bond order is higher because it is 2, so based upon that we can say that oxygen molecule is more stable molecule. And as there is a inversely proportional relationship between the bond order and bond length, and as the bond order is high, we can say that the bond length present between the two adjacent atoms in the oxygen molecule is less. So I hope you understood this particular concept of the molecular orbital energy diagram of oxygen molecule, students. Thanks for watching.